Ooh, man, I hope this works. Uh, anyway, I apologize for this being like not in person. I'm kind of there, in spirit with you, but I'm not there right now. Hopefully, you're watching this on Thursday. I am getting back in town on that Thursday um, evening, so if you want to come see me on Friday, I should be in my office and whatnot. So anyway, so for this day, first day of our advanced spec class, um, I just want to introduce the class to you. Sort of the routine is going to be we're going to sort of meet for sort of like a pre-lab lecture, at least for the first 10 weeks or so, because um, this is a hands-on class. You're going to elucidate the structure of a bunch of compounds. Two physical unknown compounds in particular, that one is going to be not that difficult. The second one might be a little bit more difficult. And then for sort of what we call the dry lab, the first three sets of dry labs, the first three dry labs are going to be just sort of problems based off of the from the textbook. The last one, I'm going to give you a natural products data sets, and you're going to figure out the structure of natural products. So that's going to be probably one of the most challenging assignments in this class. But the goal, obviously, is to get you to do a lot of hands-on NMR work. But that said, I don't want this to turn into like some sort of a lecture class. But the reason why we really have to have pre-lab lectures is, well, even when you take regular lab classes, right? Like you typically there's some pre-lab lectures to like let you know what we're gonna be doing. So even though we want to focus on the hands-on approach for you to be able to adequately use NMR techniques, especially 2D NMR techniques that you did not learn back in OChem, to be able to figure out the structure of completely unknown compounds, even the compounds, molecules that are fairly complex. To do that, the best spectroscopic method, of course, is NMR. So this class is basically an advanced NMR class. Okay, we're not going to really spend too much time on other spectroscopic methods, even though we'll spend some good amount of time thinking about mass spec a little bit because it is kind of useful. But most of our class is going to be using NMR, so um, you'll be by that magnet. And you'll be using Mystery Nova and stuff like that quite a bit. Also, you'll be looking at quite a few spectra from the NMR textbook. Hopefully you bought it already, because I want you to start working on the dry lab 1 assignment pretty much now. Okay, that's the first dry lab assignment is supposed to be mostly a review. And by the way, it's a weekend here in my office. Just to save money, I guess they shut down the heat, so like it's pretty cold in here. That's hence the jacket and everything, in case you're wondering. Thanks for asking. And I lost the train of my thought, but yeah. So the NMR work. Um, how does NMR um, how does it work first? Hopefully, almost all of this is just a review, so is dry lab 1. Um, for NMR, of course, you need this huge, gigantic magnet that's really, really strong, and so it has to be so strong that we use this really strong electromagnet. But to do that, you have to run through a ton of current. So that's why if you've seen our NMR, right, it's cooled with cryogens like liquid nitrogen and liquid helium, because at those really cold temperature, there's almost zero resistance when you run a ton of electricity through a wire. If you if you can run a ton of electricity without resistance through wires, that can produce a magnetic field that's really strong, and so that's the idea. So why do you need a strong magnetic field? Well, so that you can line up all the nuclei particles like protons um, according to the magnetic field in line with the magnetic field. Well, how do you go back to the previous slide? Wow, you can only advance when you're in this mode. Apparently, that's scary. Um, Screen recording. Yikes. That's not gonna work very well for some of the things I need to do. Why do you do that? Yeah, why do you do that? That's horrible. Okay then. Well, anyway, so once you get the nuclei particles, like the proton that you saw on the previous slide, to line up with the magnetic field, you can kind of imagine like fish if you have a fish and you put them in a river, if you have a bucket of fish, they might be swimming in any which random direction, and so are nuclei particles. They're just spinning in whatever directions randomly, normally. Once you put them in a strong magnetic field, they'll line up along with the magnetic field's direction. It's kind of like if you put a bucket of fish in a river, they'll immediately sort of line up with the current of the river, right? The same idea, except with these spinning uh, particles like protons, they can spin in the same direction as the magnetic field or exactly the opposite. It's about almost half and half, but it's not exactly half and half because it's a little bit more energetically not favored to be against the magnetic field. It's easier, it's more stable to be in line with the magnetic field, lower energy spin state. Um, and if you irradiate these with radio wavelength, radiation, you could flip the nucleus spin direction to the other direction, still lined up in the same direction as the magnetic field, and then this could sort of relax back down to the previous spin state or spin direction, and that's what we are measuring with NMR detection. It's a radio wave uh, detection. Okay? And remember those NMR signals that we observe that have gone through what's called Fourier transformation, so that it seems like a very usable signals. When you're looking at those NMR signals, you can gain four types of information. The number of signals tells you how many kinds of protons you have or nuclei you have, and where the signals appear, where the peaks appear, the location of the signals, we call those chemical shifts, right? In units of ppm, they can tell you how shielded or deshielded that proton is. In other words, it tells you the electron environment um, of the nuclei, because how likely it is, how easily those protons flip their spin direction depends on how shielded they are by electrons. So the location of the shields, the proton signals tell you how much electron density they're around, essentially. So that's useful because that can sort of translate into like what kind of a functional group it is. So already this is a lot more information than say IR can ever give. How big the proton signal is, or the area or integration of the signal, tells you how many identical protons are included in that one signal. Okay, remember the identical equivalent protons give rise to just one peak or one signal. So the area or the integration of the signal is important. I just noticed in this like webcam, I don't know if you're seeing my face too or not, which is covering part of the text, but you know, during the text on the slide, my face, I don't know which is more important for you to see for your learning. But anyway, I noticed that in that video, like, makes it look like I have more gray hair than I really do. It's kind of depressing. But anyway, the last type of information that's really, really useful. And now this, we are talking about 1D NMR right now. 2D NMR, you can gain even more information than these. But the splitting patterns of the peak tells you how many neighboring atoms or protons you've got. So that's the really powerful part of this technique. Okay. Now, remember seeing like chemical shift tables like this. This one particular one is from your textbook that I hope you bought. Depending on the chemical shifts, you could tell what kind of a chemical environment they're in. And splitting is often the most important, or maybe the confusing part. Remember, it tells you not how many protons you have on that carbon, but how many neighboring protons you have. So if you look at the signal for this proton here, right there, it's a triplet. That doesn't mean, remember the n+1 rule, right? Right. That doesn't mean that this HB, there's two protons under this peak. That just means this proton is next to two protons. Indeed, it's next to these two protons, HA. And HA, if you look at its signal, it's a doublet. That doesn't mean there's only one of these protons. It just means it has a one neighbor. Okay, so I want you to be aware of that difference. Okay, and I think we kind of talked about this last semester's or in organic chemistry class, so like you probably don't need to review this too much. Maybe I'm going to skip through this quite a bit. Um, if you wondered why, if you have two neighbors, like if you look at the signal for this with two neighbors, why you get a triplet is because each of these could have 50-50 chance of either up or down spin direction. And statistically, between two nuclei, they could be both up 1/4 of the time, they could be both down 1/4 of the time, and by about half the time, one up and one down for two. And you can think of the similar probability scenarios if you have 3 or 4, but those things follow the Pascal triangle. In other words, the integration of each peaklet is going to be 1 to 2 to 1 for triplet. For a quartet, it's going to be 1 to 3 to 3 to 1. And then if those numbers sound foreign to you, try Googling Pascal's triangle. And I'm sure in elementary school, middle school, you learned how to make Pascal's triangle once, so you can figure it out. Being able to relate splitting pattern back to coupling constants, even though you might have noticed that Nova does that calculation for you automatically, it's still important for you to know how this works to understand NMR. If a particular signal is taken on a 200 megahertz NMR machine, and the split is, say, 0.01 ppm, then the coupling constant, in other words, the how much, that's the coupling constant that's shared between the two signals that are coupled or adjacent to each other, is 2 hertz. You multiply that by the magnetic frequency, and you can get your coupling constants. Sort of the other way to think about this is the way you ended up with this 0.01 ppm separation is you divide 2 hertz by 200 megahertz. That's how you get 0.01 ppm. Now, I want you to think about this. For a 2 hertz separation of signals, if you have a more stronger magnet, let's say 400 megahertz, the separation is going to be 0.05 ppm. In other words, this separation is going to be a little tighter. And that's why with a stronger magnet, you can see even a tiny separation, and an even tiny resolution of separation means a lot. With a stronger magnet, you can, whereas if you have a weaker magnet, right, this is going to split pretty bigly, and things start to overlap. Like if this splits more, then you can imagine that would overlap with these two doublets over here, and it's going to look really, really confusing. And that's what happens with the lower frequency magnet. And that's why, you know, we are thankful that we have that big 400 megahertz NMR. And if for this split here, it's going to be 0.03 ppm separation, so the coupling constant is going to be 6 hertz. Now, this means, though, that this is split into a triplet, which is further split into a doublet. We might call this a doublet of triplets. And that makes sense because it's next to these two hydrogens, which splits it into a triplet. It has this aldehyde hydrogen that typically has a small coupling constant, so that splits each of the triplets into a doublet. So that's why you see this splitting pattern. So splitting pattern tells you a lot about its neighboring situation. Sometimes the splitting pattern could be as complex as this, but if you analyze it for a while, it's actually not that complex. This is the result of being split into a doublet by one neighbor, and that is further split into 1, 2, 3, 4, a quartet. So it has one neighbor that has one particular coupling constant, and then it has three neighbors that has a particular coupling constant, which is why it's split into a quartet here. And each of those is split by a tiny bit, tiny small coupling constant into a doublet. So how many neighbors does this signal have, or does this proton have? It's actually, we should expect to see 5 neighbors. Now you might ask, well, then how come, why don't we see a sextet or 6 peaklets, right? And that's because some of the protons have either large or small coupling constants. One proton splits by this much. One type of 3 protons splits by only this much into a quartet, and then finally one proton splits by only this much. So it's a doublet of quartets of doublets, or technically, usually people say this is doublets of doublets of quartets. So DDQ is what you might see in the literature. Here's what we mean about, like, it's better to have a high resolution NMR. This doublet of triplets will collapse to give you this, which is really confusing what's going on with a 60 megahertz machine. So praise the Lord that we have a high resolution NMR. One sort of a trick type of a thing that you might not have learned back in OChem is coupled peaks shapes typically share, if these are the assignments. Coupled peaks tend to have opposite slants, like D and E should be coupled to each other, these two triplets. And so they're indeed slanted opposite. That's sometimes useful. So this is it. This is the zoom up. That's sometimes useful to easily identify peaks that are coupled to each other, but that's not an absolute rule. So you shouldn't rely only on this to know that the two are coupled. The best way to know that two are coupled to each other, one of the ways, is to make sure that the two have the same coupling constants, or they share the same coupling constants. So A and B here also have that opposite situation. Another thing that's really important that you can derive from coupling constants is you can figure out what dihedral angle, or what angle the two neighboring protons are separated by. And like whether this is like we're talking about Newman projection type of stuff. Are they like anti 180 degrees opposite of each other, or like gauche, like 60 degrees, or eclipsed? That sort of things you can actually tell from coupling constants by solving what's called the Karplus equation. I won't require you to know the equation, it's really complex. So, but I want you to know the Karplus equation graph, what it typically looks like. And what this tells you is the dihedral angle's magnitude. It's really, really useful. And so much, it's so important that I basically will want to go over this with you again in person in maybe in the next class. But like if you had these two protons that are sort of gauche, 60 degrees dihedral angle, Karplas's equation graph tells you that you should expect a really small coupling constant. Whereas if it's anti to each other, like this 180 degrees separate, here you could expect a pretty large coupling constant. So you could tell, you could go the opposite, right? Large coupling constant, it's probably separated by like an anti situation. Small coupling constant, it might be really not separated by dihedral angle at all. So Karplus equation idea concept is really, really. Now, to review 1D NMR, proton NMR stuff that you learned back in OChem, maybe these are really great ways to review them. Sketching the predicted proton NMR and figuring out the structure from proton NMR. So those are the types of problems you find in your dry lab assignment, which if I was there in person today, I would encourage you to get started in person, and I might help you if you have questions in person, and I'm not able to do that today. I apologize, but why don't you go ahead and get started on your own, and for now you could, if you want, email me questions or whatever, but it might the easiest thing might be for you to come see me tomorrow or next week. Okay. So sketching the predicted proton NMR of this compound. I think this is part of your dry lab assignment. So if you're paying attention to this pre-lab lecture video, you actually already know the answer to some of the questions. So how do you do that? Well, I have to be careful because I haven't been able to figure out how to go back. But here's a blow-up of it. So what do you do first? The first thing you do, you should start noticing how many neighbors you have. Or that's one way to start. Like this methyl group is a CH3, but it has 2 neighbors, right? And then this is methylene, CH2, has a total of 4 neighbors, 3 and 1. So in other words, this would be split into like a quintet or 5 peaks. This would be split into a triplet, right? N+1 rule. This proton here is 1 proton. It has a total of 1, 2, 3 neighbors, so it should be like a quartet. This single proton here, remember the word is methine, right? If it's 2 hydrogens, the word is methylene. If it's 3 hydrogens, we call that a methyl group. Hopefully you remember those terminologies too. This guy has only 1 neighbor, so this should be a doublet. And lastly, this methyl group has 0 neighbors, so that should be a singlet. It's a hydrogen that's on a carbon with an oxygen, like ether or alcohol on it, so typically you expect somewhere or between 3.5 to 4 ppm chemical shift range. You might ask, how do you know? Well, you should remember when you're solving it, working with NMR, you should be obsessively looking at your chemical shift table. If you're not doing that, you're doing it wrong. This is it should be in that neighborhood, about 3.5 ppm. It's singlet, so that's what you should sketch. This guy over here is another maybe easier place to start. It's it's a triplet, right? Because it's got two neighbors, and it should be around 1 ppm because this is kind of in the regular alkane region, and it should be have enough integration for 3 protons. Same with this singlet. This is gonna be a tall, big singlet because it's worth 3 hydrogens. This is gonna be shorter than that because it's split into a triplet, right? This guy. The next one over, this would be a quintet. It's adjacent to an electron withdrawing alkene group, so it's a little more downfield, around 2 ppm. Quintet. And now between these two protons, right, like figuring out, because both of these are alkene hydrogens, thinking about which would be, relatively speaking, more upfield, which would be more downfield. Best thing to do is to think about resonance. You still can't get away from resonance. Even if you're done with the OChem, you're not done with thinking about resonance. Hopefully it makes sense to you that you could draw this resonance from that molecule, right? So what does that tell us? That tells me that this carbon here is more electron rich than this carbon. In other words, remember whether your protons appear more upfield or downfield has to do with the electron density of surrounding the protons. So this proton here, this methane, is more electron rich, meaning it's more shielded, which means it's going to be more upfield compared to this proton over here. So this is what we expect. Okay, so this would be around, like, this is exceptionally upfield olefin. Usually olefin protons, you expect them to show up somewhere between 5 to 6.5 ppm or so, but I'm predicting this to be about 4.5 ppm because of that extra electron density for this olefin. And it's got 3 neighbors total, so it should be a quartet. This one should be a double. And you want to think about chemical shift tables like this. I would have gone back and forth between these two slides, but for some reason this PowerPoint recording deal doesn't let me go back, so that's what I'm doing. And so here's this sketch, right? Like the tall singlet, little shorter triplet, both of these are worth 3 hydrogens. And signal number 4, that's also worth quite a bit because it's worth 2 hydrogens. The quintet, like we talked about. And these two methynes are smaller peaks with less integrations because they're both only worth 1 hydrogen each. One of them was more upfield right here because of the resonance, and one is more downfield. Okay, so that's the sketch. Hopefully that makes sense. The last example I want to go through with you, this is another one, problem out of your dry lab packet, or it's not a packet, but the dry lab problem sets. Dry lab 1, I'm gonna go through that one with you. It's posted on Canvas, like exactly which problems they are, as well as hints, as in like chemical formula for each of these problems, structural elucidation problems. So take a look at that. So how do you, what do you do? How do you deal with this? First, if you know the chemical formula, what should you do? Do you guys remember this? You should probably figure out the, thank you very much, the degree of unsaturation. Hopefully you remember how to calculate that. If you don't, go review your OChem notes for that, like, I can't remember, NMR or mass spec or something like that chapter. So this should have a degree of unsaturation of 1, so that means there could be a 1 ring, or there could be a pi bond. Now, if it's a pi bond, it's probably not alkene. How do I know? Well, because there's no protons around like 5 or 6 ppm at all, so I'm excluding alkene. It's very likely there's a carbonyl because we have 2 point something ppm, which is typical of a proton that's next to a carbonyl group, if you look up the chemical shift table. So that's what I'm expecting. And then what else can you tell? You can look at the integrations, and hopefully you see that this is 2 to 2 to 3 ratio, the integration curves, right? Now that adds up to 7, 2 plus 2 plus 3, but we have 14 hydrogens total. Remember, integration ratios are just that, ratios. So if you have 14 hydrogens, that means that there should be 4 hydrogens, 4 hydrogens, 6 hydrogens each. Hopefully that ratio calculation makes sense to you. And so what does that mean? So that means that this probably is 2 methyl groups, and this probably is 2 methylene groups that are identical. This is probably 2 methylene groups that are identical. And then if once you think about the splitting patterns, right, this methyl groups, or this each of these methyl group must be next to methylene, right? Because it's a triplet. This methyl is adjacent to a methylene, and likewise this peak, which is a methylene, is next to 2 protons. In other words, it's probably next to another methylene. But on the other side of this methylene, the CH2 group, there must not be any protons because it's only a triplet, right? If this also was a methylene, then this should have been a quintet because there would be 4 neighbors. Hopefully that makes sense. These guys only have 2 neighbors total. So what does that tell me? This carbon likely is your carbonyl, and that makes sense also with the chemical shift because it's around 2 point something, 2 or 3. That's usually typical of protons next to a carbonyl. What do you make of this last one? This has 1, 2, 3, 4, 5, 6 peaklets, so it's got 5 neighbors. It's a sextet. So if it's next to a methyl and a methylene, then that would be a sextet, right? So what does that tell me? That this first peak is probably this methyl. The second peak is that guy. This third peak right here is probably that guy. And then this is attached to a carbonyl over here. And it must be a symmetrical thing to account for the 14 hydrogens like this. To draw the structure more nicely, it's this molecule here, which satisfies that chemical formula. So we figured out the structure. Hopefully that makes sense to you, and please practice with the rest of the dry lab packet. And hopefully you won't have too much trouble with this because this should mostly, well, this should all be reviewed from OChem. So anyway, if you have questions, let me know, and I shall see you in person very soon. The agenda for next week, for those of you who are not in OChem lab right now, you will have to check into a drawer so you have access to glassware. So that's one thing you got to do. And then another thing, we'll start handing out your unknown compounds so you can start working on those. And especially if you, in addition, you should still have time to work on the dry lab assignment during the class time. So if you haven't finished yet after this first week, bring that with you so I can help you with it. For those of you who haven't taken OChem since we've obtained a new high-res NMR 400 megahertz, you might want to make sure that you'll get some help from me in figuring out how to use the NMR machine. I'll post the relevant pre-lab videos from the OChem class so that you can watch it and to know how to use them. I'll also share the write-up with you from the OChem lab manual, so you can know the sort of the very basics of how to operate the NMR, at least to do simple experiments like 1D proton and 1D carbon. Anything more advanced than that, we'll go over how to do those during our pre-lab lectures in our class here. So, okay. Anyway, I'm excited to do some NMRing with you, and it's a really, really interesting and neat instrument, and it's so powerful because you can figure out the structure of these tiny, smallest things in the world, molecules that you cannot even see because it's a small thing, but you can figure out the structure, and that's an amazing instrument. So anyway, that's about it for this video. See you later.